Hey y'all, so we've been talking about Big Bang and the problems with it. So here's your quick quiz to remind you about that. So we have been focusing on what happened in the past with our universe, how it started, how it expanded, inflated, all that good stuff. Now what does that mean for the future? So before we leave the sort of topics of cosmology, meaning the study of the universe and its history and its fate, let's look at the future. So the universe timeline. If you remember, we said that the universe is expanding, and from our best measurements, current measurements, that it's not just expanding, but that expansion is accelerating. So what's going to happen if the expansion of the universe keeps accelerating? So the universe timeline with expansion and acceleration. Well, we're kind of going to break this down into different eras. So we began with Big Bang and inflation. We've talked about that a lot. That was the very first fraction of a second. I don't think I said this when we were talking about inflation. I said it was a very, very early time. Well, yeah. Inflation happened less than 10 to the minus 30 seconds. That's hard to even imagine. So you put a decimal place, and then you put 30 zeros behind it, and then a 1. And that's the fraction of the second that the universe expanded to ginormous. I mean, I can't even begin to think about that. Okay, so super, super tiny right there. Very, very early times. Then we had what we call the primordial era. So the primordial era is when we have that first light of the cosmic microwave background and that time of recombination. And so in the primordial era, we only had energy in the form of radiation, and we had the first particles. Okay, at recombination, we had the very first atoms. So we had radiation and particles in the primordial era. That was the first 300,000 years of our universe. So we had super fast inflation, and then this time of recombination, first light, where we get the cosmic microwave background from. Okay, so we're up to the first 300,000 years of 13 plus billion. So right now, we live in what is called the era of stars, or more formally, the stelliferous era. So we have talked about how those first particles came together to form the first stars, and then we got these proto-galaxies forming in the dark matter halos, and those came together to form other galaxies. But all of this happened during the time of stars. So most of our universe's history has been in the stelliferous era, or the era of stars. This is the current time. That's an E. Current time, when you have stars and galaxies. Stars are forming. Okay, so this has been a very long period for us, 13 plus billion years. But it's not going to last forever. If our universe keeps expanding and accelerating in expansion, stuff is going to get farther apart, and it's going to get harder to form new stars. And when you can't form new stars, stars are going to begin to die out and not reform. So we have what we call the degenerate era. And we have come across this word degenerate before. Do you remember the degenerate carbon core? That was a white dwarf. Or the neutron degenerate neutron star. Those were the cores, the leftovers of dead stars. So that's exactly what the degenerate era is. It's the leftovers after stars die. So stars die out, you don't have any new stars forming, and you're left with these degenerate things that are just cooling. They're not creating their own heat. There's no fusion. So you have the things like the white dwarfs, and you have the things like the neutron stars, and you also have those things that weren't ever quite stars. Do you remember those guys? The brown dwarfs. So the brown dwarfs were those failed stars. So that's the kind of stuff you have. They're just sitting there. They're lumps of matter, cooling off. This will occur in about 10 to the 14th years from now. Okay, so 10 to the 14th, that's 1 with 14 zeros behind it. So we're talking past trillions here. Way, way, way into the future, when everything's too far apart to form new stars and you're just left with dead stars. Okay, so here we are on our timeline. After the Stelliferous era, we move into the degenerate era. That's going to last forever, it seems like, but not really. Eventually, all of that matter will decay. Yes, it takes a very long time for a white dwarf to decay, but eventually that matter just breaks apart into its component pieces. And the only thing that lasts longer than those white dwarfs and neutron stars are black holes. So we enter the black hole era. After the normal matter has decayed, all the carbon and all those things, it's gone. And we are left with only black holes. A universe of only black holes, getting farther and farther apart from one another. And we used to think that black holes didn't decay, but now there's some idea that in fact they do. It's called Hawking radiation, if you're interested. And so they'll be around for a super long time. The black hole era will come in about 10 to the 39 zeros years from now. And it will last way, way longer than that. Like, the black hole era is huge because it takes a really long time for a black hole to evaporate, even longer than for a neutron star or a white dwarf to decay. But eventually, we may reach a point, well, not we won't be around anymore. The universe will reach a point of what is known as the dark era. In the dark era, even the black holes are gone. That was the last structure that is left, so there's no structure anymore. Black holes evaporate. And what are we left with? Only a few random particles. Only leaving particles. The energy is so spread out that there's no light, there's no radiation, so to speak. You just have pieces of atoms floating around. Very, very cold. Everything. A little depressing, but like I said, we'll never make it there. This is so far in the future. 10 to 100 years. But that's where we think our universe is heading if it continues to expand and accelerate. Alright, so how do we summarize the final state of our universe? Take a look at these, answer your clicker question.